Welcome to this second part of the video. Here I'm going to talk to you about two real-world examples where we've tried to implement the concepts that we talked about in the first part of the video. Now, both of these examples are described fully in worked example reports that can be downloaded from the GMDSI website. The first example is a mining example. This pertains to the Pilbara area in Western Australia. The geology is complex, steeply dipping beds, Precambrian beds, some of which the hydraulic conductivity is high and separated from other beds in which it is low. And this is the bed in which a mine at that time was to be built, but the mine is now in operation. Prior to the digging of the mine, a model was built in order to look at a couple of things, and that's where things started going wrong. It was being asked to look at too many things. One thing it was being asked to explore was dewatering requirements for the proposed mine. Another thing that it was being asked to explore was the effect of that dewatering on groundwater dependent ecosystems at some distance from the mine. So the domain of the model was large. The model was built according to the traditional way of doing things that I talked about in the previous video. Respect for prevailing geology was very high on its agenda. 7 layers the model had, a fairly fine grid within the mining area, and more coarse as we went further afield. Now, there's problems encountered in replicating geology or attempting to replicate geology that's this complex. Steeply dipping creates a problem. And also what creates a problem is that it's a moving target. As more wells are drilled and more is found out, the geological model changes. Another problem too is that the area is pervaded by structural features which we now know play a considerable role in movement of groundwater. So being faithful to the geology, well, firstly it's a moving target, and secondly, well, you're never quite sure what you're being faithful to, and thirdly, representing steeply dipping geology in a numerical model is hard. The model was history matched against water level data, which we'll talk about shortly, in the area of the mine. It didn't do a very good job of fitting that data, nor did the model do a very good job of predicting dewatering requirements. 2 years ago, a colleague of mine and myself were asked, can we demonstrate perhaps a better way of processing the type of data that's gathered in areas such as this that may be information rich in questions they want answered, such as what are the dewatering requirements for the mine. In this case, the data consisted of 6 week-long pumping tests in wells that you can see here, and observations of drawdown in about 20 other wells. What information can we extract from drawdown data that can tell us something about dewatering requirements of the mine, which is now in operation in this area here? So we used a single layer, a grid constructed using algo mesh, following the precepts of structurally simple, parametrically complex. Most water flows horizontally here, even though the geology is complex. We decided and we hoped that a single layer fast running model would enable us to extract the information we needed from the data that resides in these drawdowns. So we equipped the model domain with 1,500 pilot points, and these were used to carry hydraulic conductivity and specific yield parameters. The model runtime was quite short, about 1.5 seconds, so we can do magic in terms of data assimilation and predictive uncertainty analysis. Fitting the drawdowns that emerged from the 6 pumping test was easy. The black dots are measurements, the blue lines is what the model produced. We were able to replicate the ups and downs really well. These coloured bars signify when a well was pumping. So here's the hydraulic conductivity field that emerged from history matching. Now I've overlain it on a satellite image here. These lines here are structural features that may or may not exist in the area. You can see that geological map underneath, and here I've done linear uncertainty analysis. The brown indicates where uncertainty reduction was the most. So we can see that some of this pattern coincides with the geology. Some of this pattern coincides with structural features. These patterns are to be believed because the uncertainties are not very high. Something is going on here, it's structurally controlled, it's also controlled by the stratigraphy. Here's specific yield. Well, again, some of these features I can relate to the stratigraphy, the ironstone here and the dolomite here. This is the ore body up here. This one here was more problematic. What's causing that? Now, it needs to be believed because the uncertainties are low. Perhaps this is due to a structural connection with an overlying tertiary aquifer. In either case, it cannot be ignored. So what then have we learned from this history matching exercise? Have we learned that this is the disposition of hydraulic conductivity and specific yield under the ground? No. That's too complicated. I can't infer that from this amount of data, but what I can infer are some pretty important things. I can't infer the exact disposition of hydraulic properties, but I can infer that they are both geologically controlled and structurally controlled. They're both stratigraphically and structurally controlled. That means that flow of water is going to take place along some of these structures, and it will deliver water, a considerable amount of stored water, to the area where the mine is going to be dug. So while I don't know exactly what's going on under the ground, I know the repercussions for the thing that I care about what's going on under the ground. If I use this model to predict dewatering requirements, they actually turn out to be pretty much in line about what's being experienced now. So using this model that was targeted to assimilation of data that was pertinent to a prediction that I needed to make, I was able to obtain information from that data that enabled me to say some pretty important things. Water will flow to this area through stratigraphy and through structure, and that dewatering requirements are going to be higher than would have been predicted and that were predicted on the basis of the previous model, that modelling work that was done according to the traditional philosophy that we spoke about in the first of these videos. In this second example, we looked for sources of contamination. So this is a map of the town of Pavia in northern Italy. The town is underlain by alluvial sediments, and within those sediments, contaminants have been detected, PCE, TCE, and other contaminants. We built a model whose task was to explore the possibility of identifying the sources of those contaminants. Now, looking for a contaminant source is kind of an inverse problem on steroids. We want to back calculate the source of contamination, but at the same time we want to back calculate some of the hydraulic properties of the medium, the porous medium, through which that contaminant and groundwater has flowed to get from the source to observation wells. And in some of those observation wells, contaminant has been detected, those that are marked red. In some, it has not been detected. In all of these observation wells, we have had measurements. That is the data set that exists for history matching. How much information can we get out of that data set in our search for sources of contamination and the properties of the medium through which water and advected contaminant flowed? So we built a model, a one-layer model in this case. There aren't any issues here with contaminant moving from one layer to another, so one layer is sufficient, structurally simple, parametrically complex, as we've been talking about up to now. Pilot point parameters are assigned all through the model domain, and also pilot points are used for parameterization of boundary conditions. We don't know these exactly. If we don't know something, let it wiggle, let it be a parameter, let it be constrained by expert knowledge and the necessity for the model to replicate historical conditions, but don't hardwire things in that we don't quite know. So once again, structurally simple, parametrically complex, constrained by all the data that we have available. So here, once again, is our data. We have wells which have detected contaminant and those which have not. Now, concentration data is notoriously difficult to use for solving an inverse problem. Concentration measurements are very variable. Vertically, laterally, they're very noisy, very messy. So they are not the ideal candidates for back calculation of things, either hydraulic properties in a model domain or contaminant sources. And use of an advection dispersion model is not a very good idea either. That has problems. Use of an advection dispersion model to calculate concentrations to match against measurements is problematical because it takes a long time to run. We have to have a source from which the contaminants emerge, and we don't know the source. And the concentrations which are calculated tend to be smudged and therefore difficult to match to field data because of numerical and hydrodynamic dispersion. So we adopted a different approach here. Firstly, our observations. We categorized our observation wells into two types: whether they had detected a contaminant or whether they did not detect a contaminant. Processing of data was made a little easier by the fact that the steady state flow conditions could be assumed, but the methodology, which I'm about to explain to you, does not require that we adopt a steady state assumption. It's quite general. But in practice, if we've detected a contaminant, we can't really match the concentration with a model. About all we can say is that at this time, the time at which we had detected the contaminant, it was in the plume. So the most we can say is, am I in the plume or out of the plume at a certain time? And on that basis, we subdivided our observation wells into two types. And then, instead of using concentrations calculated by an advection dispersion model, we used particle paths. We released particles all throughout this model domain, thousands of them, and they could flow where the groundwater flow field took them. So here's the source cell of a particle, and here's a particle. And our aim is to advect this particle through the flow field, gather information from the proximity of the particle to either detect wells or non-detect wells, and then transfer that information back to the sources of the particles. That way we capture information from contaminant measurements, and that information is used not just to try to calculate contaminant sources. It can also be used, as we'll show in a moment, in the model calibration process through which hydraulic properties are inferred, and it can be used in conjunction with more traditional data such as heads that are used for calibration. So here we have a source of a particle, a cell in which a particle has been released, and it may or may not pass close to wells in which contaminant has or has not been detected. Notionally, we say there's a little halo that exists around that particle. And that halo decays with distance from the particle trajectory as a Gaussian function. So that resembles the analytical solution to the advection dispersion equation. We then assign a status to each particle, and there are thousands of these particles. If a particle passes close to a well in which a contaminant has been detected, it inherits a so-called detect status from that well, and the influence of that well on the particle status decays with this Gaussian function. So it's a continuous function. Our particle track, and hence our particle's status, is a continuous function of proximity to a well and hence to the parameters of a groundwater model. Hence we can use it in calibration of that model. So each particle has a trajectory which, depending on the proximity, the distance of closest approach of that trajectory to a detect well, may be awarded a status which we call a detection status. If it passes close to a detect well, its detect status is high. If the particle passes close to a non-detect well, its non-detect status is high. If it passes close to no type of well, it has neither a detect status nor a non-detect status. Well, it has a 0 for both of those. If a particle passes close to both a detect well and a non-detect well, it is endowed with an inconsistency status. That can't happen. The particle either carries mass with it or it does not. So we have a measure then of the extent to which a parameter field is at odds with our contaminant concentration data. If a trajectory has a high inconsistency status, the parameter field needs to be adjusted so that it doesn't. So of the thousands of particles that we release within this model domain, each particle has a detect status, a non-detect status, and an inconsistency status. We add to our observation data set the things which PEST uses to back calculate hydraulic properties. We add to our observation data set an observation pertaining to every single particle that we release in the model domain. And that is the observation that its inconsistency status is 0. So PEST is then able to adjust hydraulic property fields so that we fit heads and that no particle has a non-zero inconsistency status, which means It passes close to one or more detect wells, close to one or more non-detect wells, past to neither, but not close to both. So we include this in the calibration data set, and the calibration process ensures that each particle has a zero inconsistency status. Once we have consistent particle tracks, we can pass that status back to the source of each particle. And we can have a particle released in every model cell if we like. Thereby, each model cell from which a particle originates is awarded a detect or non-detect status, which can be zero if the particle path passes near no observation well that detects contaminants or no observation well that does not detect contaminants. That is, passes near no observation well. So, this is used in history matching. This is used for making predictions. So we calibrate the model. Here's the heads calculated by my calibrated model. Here are particle paths that have a non-zero detect status. Here's the hydraulic conductivity that emerges from the calibration process. This is calibrated against heads and against particle track consistency. Here is recharge calibrated against the same data. So now I have a parameter field that allows the model to respect heads and allows the model to respect contaminant concentration measurements, including contaminant concentration measurements of zero, that is, non-detect. I then repeat this process 300 times using the PEST PP IES Ensemble Smoother. So now I have 300 parameter fields, all of which allow the model to respect head observations, all of which have internally consistent particle paths. Therefore, they allow the model to respect concentration observations. So then I can start to build up some source statistics. So let's take the detect status statistic first. It is awarded to each particle trajectory. It then gets transferred to the source. So the particles are helping us to take information back from the observation points to the source. I have 300 parameter fields, all with particle tracks, thousands of particle tracks that are consistent and that respect all available information. I can accumulate the source statistics to build up a probability map. In this case, I'm taking those detect statistics and I'm calculating 1 minus detect statistic awarded to each particle, each model cell over all 300 realizations. And you can show that what we can calculate is a probability distribution for each cell. I'm calling this PSND. This is a map of the probability that if a contaminant exists, a contaminant source exists in any particular cell, then it will not be detected by the existing monitoring network. The probability that a contaminant at any place will escape detection. Blue is better because blue says it won't escape detection, and that happens right up against, just upstream from detect wells. From the other statistic that is awarded to particles and then transferred back to source cells, I can calculate Another statistic, a water to source cells, averaged over all parameter fields. This is the probability that a source does not exist in each one of those cells. Once again, blue is better. The probability that a source does not exist is greatest just upstream from a non-detect well. So now I have two probability maps that summarize just about all I can know about from the information that I've got at hand. They're probability maps, so they make it explicit that there's a lot I don't know, but they make it also explicit where I can know stuff and what I can know. In this case, the probability that that contaminant will go undetected, PSND. In this case, probability that there is no contaminant source, PSNE, in this particular cell. Excuse me. Now notice too that both of these probability maps embody a negative. In this case, it's the probability that a source will go undetected. There's a negative there. In this case, it's the probability there is no source. Remember we said at the beginning of the first video, the scientific method, the Popperian view of the scientific method, the falsification view. The fact that we don't know what happens, we can only know what doesn't happen. These probability maps are quite in harmony with that view of knowledge expressed by that exposition of the scientific method. So this is about as much information as we can get. This is about as much as we can say from the data that we've got at hand, and this was extracted from that data using a model built to solve an inverse problem, a very difficult inverse problem of inferring hydraulic properties and of back calculating contaminant sources. We can go a little bit further here. I can now ask, well, what information should I gather next? I can use this same methodology to answer that question. Suppose that I'm interested in this area here. Should I drill a well here or here? If I drill it close, I can get focused information, but only over a small area. If I drill it further away, I can get more spread out information over a larger area. How do I measure the worth of drilling in one place or the other? Well, it's not too difficult. I've got my particle paths. I can just recalculate statistics awarded to those paths. I can recalculate particle statuses. I can transfer those statuses to the cells in which the particles originate. Over 300 parameter fields, I can draw revised probability maps and see what that information will tell me. So I can focus on this well here, and I can focus on the PSND statistic. I can say, what is the difference between that probability integrated over all of this area between me detecting a contaminant here or not detecting a contaminant here? That integrated difference is the information content of that measurement with respect to this polygon. For this particular well, it's 0.019 out of a maximum of 1. For this well, it's 0.056 out of a maximum of 1. This is the better well to drill. I can do the same thing for the other statistic, the PSNE statistic. I can recalculate probabilities over this area on the basis that I do or do not detect contaminant in this well. The difference between integrated probabilities under both of those assumptions is a measure of what this will tell me when I drill this well and see whether there's contaminant there or not. For the southern well, it comes to 0.018. For the northern well, it comes to 0.060. Once again, this is the better place to drill. So, using a model built specifically to process data in ways that are focused on something that I need to know, I have been able to extract from that data information which can tell me all that I can know given the data that I currently have at hand. So on to conclusions. Well, we as human beings are not very good at simulating subsurface processes, replicating subsurface hydraulic properties. That's the bad news. But it's really not that bad, because the good news is we don't have to. Our job is to provide information that decision makers can use that are based on the repercussions, not the actualities, of those subsurface properties and processes. Our job is to process data and extract information that's available to provide to a decision maker a summary of what can be known and what cannot be known given available data. The decision maker has a hypothesis that she needs to test, that of something going wrong if a particular course of management action is taken. The information that we process may or may not allow him or her to reject that hypothesis. Either way, he or she has at his disposal what is needed to make a decision. Our job is to take that information and to transfer it to where it is needed. Our job then is similar to a transmission line. Here's information. It's a little bit hard to get at. With simulation combined with PEST and PEST++, we can get at that information. We can encode it in model parameters. We can transmit it to a place where further processing, probably probabilistic in nature, as you have just seen, where a decision maker using common sense can then use it to make a decision. Normally, as I have said, the transmission line will be comprised of a structurally simple, parametrically complex model. A model that can harvest and convey information and then present it in ways that a person can understand, because it's a person who has to make the decision. How we do this? It's subjective. It is an art, but it's also science. And that's the thing. What I've tried to say through these two videos is that our job of information harvesting and transfer will be subjective. It will require skill, but we do have a point of reference. And that point of reference is the scientific method. And perhaps in the field of groundwater, a little bit more inspiration can often be drawn from the Popperian point of view than the Bayesian, on account of we have so little prior information, we have so little basis for forming prior probability distributions, but we do have hypotheses presented to us on a silver platter which we need to test, and we can build scientific instruments from groundwater models and PEST++ to test those hypotheses and allow decisions then to be made on a much more scientific basis than they are presently being made. Thank you for your attention.